So we were discussing about what happens when we have a tie. Okay, so what is a tie? Tie is when you have a problem in deciding who is going to be the entering variable. Okay, so here we have an example of a simplex table given. Okay, we have the Cj minus Zj. It is based on Cj minus Zj that we decide the entering variable. Okay, over here we have Cj minus Zj. We will go for the greatest value. Okay, so here we have 2.5 and again 2.5. So there is a tie. We will not be able to decide whether the entering variable is going to be x2 or is it going to be S2. Okay, x2 or S2. Okay, so what is x2 called as? X2, x1, all of such variables are called as decision variables. Okay, and S1, S2, all such variables are called as slack variables or surplus variables. Okay, slack and surplus variables, they are represented by the same symbol S. Okay, so we are having in this problem, we are having a decision doubt over here, that is whether it is x2 or S2, it is going to be the entering variable. Okay, in such cases, what do? We will always go for the decision variable. Okay, so decision variable will be chosen to enter into the basic. Okay, hope you remember how we solve the simplex problem. We will decide for the entering variable and that entering variable will replace the leaving variable. Hope you remember that, right? So in this case, what will happen when we have a doubt whether or when we have a tie between a decision variable and a slack variable, we'll always go for the decision variable. Okay. Other than that, when you have, suppose here x1 is there, x2 is there, both are decision variables. Okay. If you have a tie between the decision variables, okay, if you have a tie between two decision variables, in such cases, we will go for any of them. Any of them can be chosen at random. Okay. Either you can choose x1 to be the entering variable or you can choose x2 variable. Okay. So what happens when the slack variables are having a tie? For example, S1 and S2 is having a tie. What will you do in such cases? In such cases also, you can choose arbitrarily. Okay, anyone can be chosen to be the entering variable. It can be S1 or it can be S2. There is no problem. Okay, but when you have a tie between the decision variable and a slack variable, in such cases, you have to go for the decision variable. Is it clear? Okay, so that is what happens when you have a tie for the entering variable. Okay, it is given in the table over here. When you have the tie between two decision variables, we can choose it in random. Okay, similarly, when the tie is between two slack variables, or it can be surplus variables also. Okay, when there is a tie between two slack or surplus variables, we can choose the entering variable in random, okay, or arbitrary. Anyone can be the entering variable. But when we have a tie between a decision variable and a slack variable, okay, or when we have a tie between a decision variable and a surplus variable, in such cases, we have to choose the decision variable. Okay, they are represented by x1, y1, x2, y2, or x and y, such variables. Okay, so we have to select the decision variable as the entering variable. Okay, hope it is clear. Now we have seen what is a tie for entering variable. Okay, tie for an entering variable. Now we are going to see what happens when you have a tie for a leaving variable. See here, leaving variable. So what will happen when you have a tie for a leaving variable? Okay, so we'll see what happens. Just read through. Two or more elements may have same positive value, okay, least positive value for minimum ratio. Okay, we decide the leaving variable based on the minimum ratio, right? So when minimum ratio, there is a tie between two variables and the two variables have the least positive value, then there is a tie. Okay, we have to decide which is going to be the leaving variable. Okay, in such cases, or when we are having the solution, okay, solution as 0. Okay, so when we have the solution as 0, how do we decide the minimum ratio? It is solution divided by the key column, right? Okay, when we divide it, any value 0 divided by any value in the key column, you will get the answer as 0 itself. Okay, if so, if two or more values in the solution or xb, okay, for example, over here, just take this case itself over here. If the solution over here is 0, for example, just take it. Okay, in this case also it is 0. Okay, in such cases, what will happen? You will have 0 divided by, this is going to be the key column. Okay, 0 divided by 0.5, and here also it becomes 0 divided by 0.5, which is 0. This is also 0. Okay, here also we are having a tie. Okay, we are not able to decide whether S1 is going to be the leaving variable or X1 is going to be the leaving variable. We are not able to decide. Okay, in such cases, what we will do? Okay, that is what we are going to see next. Okay, this kind of problem is called as the problem of degeneracy. Okay, it is called as the problem of degeneracy. Don't forget, degeneracy means when you have a tie for the minimum ratio. Okay, in two situations you will have a tie for minimum ratio, and when you have the same minimum ratio or when you have 0 for the solution. Okay, just now I showed you when the solution column or XB column, when they have 0, okay, and you divide it by the key column, you will have again the minimum ratio as 0. Okay, so any two rows, if they have 0, okay, then we have a tie. Okay, that is what I just now showed. Over here you have two rows having the same value 0. Okay, so they are having a tie. Okay, such a situation is called as the degeneracy. Okay. Further, we'll see the problem usually arises due to redundant constraint, that is, one or more than one of the constraints are not part of the feasible region. Okay, such a situation of degeneracy happens when there are redundant constraints. Okay, or in other words, the LPP is not formed properly. Okay, the constraints are not correct. Okay, that is why you will have the problem of degeneracy. Okay, now there is steps so that how to solve a degeneracy problem. Okay, it is not as simple as the previous case when we decided arbitrarily or we gave more preference to decision variables. It is not so easy in this case. Okay, so we'll solve it using a problem. Okay, hope it is clear till now. We'll solve using a problem. Okay, here we have an LPP. Okay, for explaining degeneracy problem. So degeneracy is when you have a tie for a minimum ratio. Okay, tie for the minimum ratio. So here we have an LPP. There are three constraints here. Okay, so I have already written a few so that I can save time. Okay, since the LPP is not in the standard form, okay, we need to convert it into the standard form by introducing slack variables. Okay, here we have the simple less than or equal to. Okay, so we have to add the slack variable S1 to this constraint. Again, for the second constraint also we have less than or equal to. So I'll be adding the constraint S2 to this constraint, okay, to this inequality, to remove the inequality. Again, for the third constraint also I have less than or equal to. So I'll be adding the slack variable S3, okay. And if when I've added S1, S2, S3 to the constraints, what I should do? I should introduce them into the objective function also. Okay, so all this has been done over here. Max z is equal to 2x1 plus our previous maximization equation is max z is equal to 2x1 plus x2. So here I have 2x1 plus 2x2. Okay, just give me a second. This is x2 only, okay. Yeah. So here I have 2x1 plus x2. Over here I have 2x1 plus x2 plus we have to introduce the three variables there, s1, s2 and s3. They will be having 0 coefficients. Okay. So our objective function is over. We have the constraints here with each of the, okay, I'm sorry. Here I will not have 0. I will have one s1, one s2 and one s3. Okay, these are the slack variables, okay, added so that we can remove the inequality. Okay, so now we'll introduce all these constraints and the objective function into the simplex table. Okay, we have Cj. So what are the coefficients of Cj? Here we have 2, then 1, 0, 0 and 0. Okay, 2, 1, 0, 0 and 0. Then what are the variables of those coefficients? It is x1, x2, s1, s2 and s3. So we write over here x1, x2, s1, s2 and s3. Okay, here we have basic variable represented by b. Here we have the coefficient of the basic variable. Here we have the value of the basic variable. It is represented as solution or it is represented as xb. Okay, here we have the minimum ratio. Okay, is it clear? Okay, now this is going to be the body of the constraints. We'll be entering each of those coefficients of the constraints. Okay, 4, 3 and 1 for S1. So here I have 4, 3, S1 is 1. I don't have value for S2 and S3. Similarly, 4, 1 and S2 is 1. Okay, so here I have 4, 1, 0 for S1. Here I have S2. Okay, so I put 1 there. 1 is the coefficient of S2 and I don't have S3, so I put 0. Okay, similarly, here I have 4 minus 1. Here I have S3. Okay, 4 minus 1. I don't have value for S1, so I put 0. S2 also I don't have, I put 0. S3 I have. The coefficient of S3 over here is 1. Okay, now what are the solutions? 12, 8 and 8. Okay, 12, 8 and 8. Now how will you consider, how will you decide the basic variables over here? You have to check for the identity matrix. So here we have 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so corresponding to the first row, the basic variable is going to be S1 with coefficient 0. Okay, so S1 and coefficient 0. Here, second row, I have 1 in this second row. So the variable that is going to be the basic is S2. Okay, S2, 0. Similarly, in the third one, we have S3 and 0. Okay, now what do? We go for Zj. How will we decide Zj? We multiply each of the values in CB column with each of the columns of the simplex table. Okay, so here 0 into 4 plus 0 into 4 plus 0 into 4, that is going to be 0. Okay, similarly, each of the values are going to be 0 because our CB column is completely 0. Okay, so when we multiply it, everything is going to be 0. Okay, next one is Cj minus Zj. Cj is what we have over here. Okay, so 2 minus 0. 2 minus 0 is 2. Okay, 1 minus 0, 1. 0 minus 0, 0. 0 minus 0, 0. 0 minus 0, 0. Okay, so now we have to decide for the entering variable. How will we decide the entering variable? Entering variable is going to be the highest positive value in Cj minus Zj. Okay, over here it is 2. So we'll be selecting this column to be the entering variable. Okay, this is going to be the entering variable. Next, we have to decide which is going to be the leaving variable. For that, we have to calculate minimum ratio. How will we calculate minimum ratio? It is calculated as xb. This is xb column. Okay, so xb divided by our key column. Key column is x1. Okay, x1. So minimum ratio is going to be 12 divided by 4. 12 divided by 4, 3. Okay. Now 8 divided by 4, that is 2. Again 8 divided by 4, that is 2. Okay. Now tell me which is going to be the leaving variable. Leaving variable, we decide it using the least positive minimum ratio. Okay, least positive minimum ratio. In our case, we have over here 2 and here also we have 2. Okay, in such cases, what will we do? We have a tie over here. Okay, so we have a tie for the second row and the third row. So we are not able to decide which one, S2 or S3 is going to be the leaving variable. We are not able to decide that. Okay, in such cases, what will we do? So we have to follow the steps for solving the tie for a degeneracy problem. This situation is called as a degeneracy problem. When you are not able to decide which row or which variable to be the leaving variable. Okay, such a situation is called as a degeneracy problem. Okay, in such cases, what will you do? Okay, you have to follow the following steps. Here, just tell me what is the identity matrix over here. The identity matrix is formed by columns S1, S2 and S3. Correct, right? Here we have 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is going to be the identity matrix. Okay, here we have the identity matrix. Okay, this row we don't have to consider because we don't have a tie here. Okay, we have a tie for the second and the third row. So in this identity matrix, we don't have to consider this row. We need to consider only the second row and the third row. Is it clear? Because we have a tie only for the second and the third row. Okay, we don't have to consider the first row in this identity matrix. Okay, I don't have to consider that. Okay, now you take the second and the third row. Okay, in that you take the first column. The first column is formed by this 0 and 0, this 0 and this 0. Okay, in this identity matrix, first row you don't have to select because you don't have a tie there. Tie is between the second and the third row. Okay, so you take the second and the third row in the identity matrix. Okay, so this is the identity matrix that you have to consider. Okay, in that you take the first row. First row you have the element 0 and 0. Okay, divide this first column by the key values. Okay, key column. This is the key column. So divide 0 by 4. What is 0 divided by 4? Okay, so what I'm doing over here is S1 divided by X1. Okay, X1 is the key column. Okay, over here, I don't have to consider this value because I don't have a tie here. So I'll put a dash there. Okay, over here, it will be, the solution is 2. No, sorry, I have to divide this value. Okay, this is 0. The elements of the identity matrix is what I have to consider. So 0 divided by 4. 0 divided by 4 is 0. Okay, again, here 0 divided by 4. So 0 divided by 4, I have 0. Okay, now what happened? Again, I am not able to decide because again I have values 0 and 0. So again, I am not able to decide which is going to be the leaving variable. Okay, so again I have to repeat the same step. So first column I have already considered. Since I was not able to decide which is going to be the leaving variable, there is a tie again. So I will go to the next column. Next column has the values 1 and 0. Okay, so I will divide it. Next column means it is S2. So S2 divided by which column I have to divide it with? X1. X1 is the key column. So I will divide it with X1. Okay. So here I'm considering X2. Here I have 1. 1 divided by 4. Okay. So 1 divided by 4. Next one, 0 divided by 4. 0 divided by 4. Okay. 1 divided by 4, I can keep it like that. 0 divided by 4, the answer is 0. Okay. So here, which is the least positive value? The least positive value in this minimum ratio is this one, right? Here I have 0, here I have 1 by 4. So in this, comparatively 0 is more least positive value. So I'll be selecting the third row. Okay. So I'll be selecting the third row as my leaving variable. So S3 is going to be the leaving variable and X1 is going to be the entering variable. Okay, so clear now? So this is how you solve a problem when you have a tie for the minimum ratio. Okay, consider the identity matrix that is corresponding to the rows that has the tie. Okay, consider the identity matrix. In that you select the first column, divide the elements of the first column with the elements of the key column. Okay, then you will get the answer as 0 and 0. Here again I am having a tie. So leave the first column, go to the second column in the identity matrix. Okay, divide each of the elements of the identity matrix in the second column with the elements of the key column. Okay, over here I have 1 divided by 4 and 0 divided by 4. The answer is 0. So in this, comparatively 0 is most least positive. Okay, so I will select the third row to be the leaving variable. Okay, in our case we have S3 as the leaving variable and X1 as the entering variable. Is it clear now? Okay, so this is how we solve the degeneracy problem. Okay, when you have a tie. Okay, so now I have already written few steps. So the leaving variable in our case is, leaving variable is S3. Okay, entering variable is going to be X1. I have already written that leaving variable is S3, entering variable is X1. Okay, we have to perform the following row operations. First, we will solve for the key row. Okay, key row is the third row. Okay, so R3 new is equal to R3 old divided by the key element. Key element over here is 4. Okay, the intersection of the key row and the key column will give you the key element. Okay, key element is 4. So I am dividing R3 new is equal to R3 old divided by 4. Similarly, R1 new is equal to, I am considering the first row. Can you see the first row? First row. So R1 new is equal to R1 old minus, which is the element above or below the key element here. When I'm considering the first row, it is 4. Okay. So over here I have written 4 into R3 new. R3 new is nothing but our new key row. Okay, so that is R3 new. Okay, similarly, I have to change the second row also. Okay, for that I have R2 new is equal to R2 old minus. When I'm considering the second row here, what is the element that is above or below the key element? Key element is 4. The element above the key element is 4. Okay, when I'm considering the second row. Okay, so here it is 4. Okay, so I'm writing over here also 4 multiplied by R3 new. R3 new is again our key row. Okay, new key row. This is our new key row. Key row new. Okay, R3 new, it is key row new. Okay, over here R3 new means this is going to be the key new row. Okay, so we have all the three operations written down. I have already done that, and then to save time, because we already have done multiple problems on the simplex. Okay, so I have filled the first iteration. Okay, after doing all these row operations, I get the values to be filled. Okay, in all this. Okay, here we had leaving variable as S3 and entering variable as X1. See over here, I have put X1 instead of S3. Okay, the coefficient of X1 was 2. So I entered this one over here. S1 and S2 will remain the same. The other values I have entered using the operations, the three operations which we have computed here. Okay, so this is the value. These are going to be the solutions. So after getting all this, we will be calculating for Zj. After getting Zj, we will calculate Cj minus Zj. Okay, hope this much is clear. Then we will go for deciding. According to Cj minus Zj, we will decide which is going to be the highest positive value here. In my case, 3 by 2 is the highest positive value. The other values are 0 and negative values, so I'll ignore them. So this is going to be the key column. So x2 is going to be the entering variable. Okay, now I have to decide which is going to be the leaving variable. Okay, leaving variable, how will I decide? I have to calculate the minimum ratio. Okay, minimum ratio, how will I calculate it? I have to divide xb divided by the key column, that is x2. x2 is the key. x2 is the key column. Okay, so here I have 4 divided by 4. What is the answer? It is 1. Over here I have 0 divided by 2. 0 divided by 2, which is 0. And here I have 2 divided by negative 1 by 4. See, minimum ratio, we have to enter only positive values. So here I am getting 2 divided by negative 1 by 4, which is a negative number. So I will not enter it into the minimum ratio. Okay. So here I have 1 and 0, which is comparatively least positive. 0 is least positive. So this row is going to be the leaving variable is going to be S2. Okay, so S2 will go out and X2 will come inside. Okay, I selected this problem so that you will not make a confusion. When you have 1 and 0, you don't have to confuse yourself. 0 itself is the least positive value. Okay, 0, you don't have to ignore 0 here. 0 is the least positive value, so you have to select the second row. Okay, so once that much is done, we already found out that our outgoing vector is S2. See, x2 is going outside and incoming vector is x2. Okay, incoming vector is x2, and then we have to perform the row operations. Okay, row operations, first we will start with the second row because that is our key row. Okay, here what we have to do, the key row will be divided by the key element. Key element is 2. Okay, so I have written there R2 new is equal to R2 old divided by the key element, which is 2. Okay, next we have to change the first row. First row is R1 old. Sorry, R1 new is equal to R1 old minus over here, which is the element that is above or below the key element. Key element is 2. When we are considering the first row, the number above the key element will be taken into consideration. Over here it is 4. Okay. So over here I have R1 old minus 4 into R2 new. Similarly, when we are considering the third row, I have R3 new is equal to R3 old minus what is the value below the key element? It is minus 1 by 4. Okay, minus 1 by 4 into R2 new. R2 new is nothing but our new key, this one. Okay, sorry, this one, R2 new. Okay, so R2 new is nothing but our new key row. Okay, So once we have all the three operations, I have the values. To save time, I have already written them. Okay. So over here, instead of S2, I have X2. Okay, the value of the coefficient of X2 is 1. So I have written that. S1 and 0 will remain as same. Okay, these are the values that I got through the row operations. Okay, I have already calculated Zj. Okay, and Cj minus Zj also. In this case, we have to go for the most positive value of Cj minus Zj. Over here, I have 1 by 4. So 1 by 4 will be the column corresponding to 1 by 4 will be the entering variable. Over here, my entering variable will be S3. Okay, now I have to decide for the leaving variable. How will you decide it? You have to calculate the minimum ratio. Okay, over here I have the minimum ratio. It is XB divided by S3. Okay, so it is, here I have 4 divided by 1. Okay, 4 divided by 1, which is 4. Okay, next one is 0 divided by minus 1 by 2. Okay, do I have to enter the value as 0 in the minimum ratio here? Do I have to enter it as, because any value, any number which is 0 divided by any other number, it will be 0 itself, right? But in this case, our element in the key column, okay, that is minus, it is a negative value. So always remember, when the number that is to be divided is a negative number, you don't have to enter anything into the minimum ratio. Is it clear? Even though the numerator is 0, if you're going to divide that numerator by a negative number comes from the key column. Okay, in such cases, don't enter anything into the minimum ratio. Okay, make it very sure. Please make a note of it. That is why I took this question itself, so that I can show it to you. Okay, so I don't have to enter anything over here. Once more, I'll repeat it. Okay, any value 0 divided by any other number, you will get a 0 itself. Okay, that is the common method that we have seen. But in this case, in the case of simplex, okay, when you have a value 0, which is going to be divided by a negative number, which comes from the key column, don't enter anything into the minimum ratio. Okay, don't enter anything. So 0 divided by minus 1 by 2 is actually 0 only, but don't enter anything because the value in the key column is negative. Hope it is clear. Okay, next one is 2 divided by 1 by 8, which is 2 into 8, which is 60. Okay, here we have the least value as 4, so we'll be selecting this as the leaving variable. Okay, so S1 is going to be the leaving variable and S3 is going to be the entering variable. Okay, see over here, I've already written outgoing vector is S1. S1 is going to go outside, and who is going to come inside? S3 is going to come inside. So incoming vector is S3. Perform the row operations. Just tell me the operations. First, we'll start with the first row because that is the key row. Okay, key row has to be divided by 1. Okay, because 1 is the key element. Okay, so you don't have to do anything. The key row will remain the same because all the values are getting divided by 1 itself. So don't do anything. Next, we have to go for R2. Okay, R2 new is equal to R2 old minus what is the value just below the key element? It is minus 1 by 2. So you have minus 1 by 2 into the key row. Okay, key row new. Okay, key row new and key row new old is the same in our case, in this case. Okay, next one R3. R3 is equal to R3 old minus what is the value below the key element? Key element is 1. The value below the key element corresponding to the third row is 1 by 8. So we have 1 by 8 here. Okay, 1 by 8 here into key row. Okay, key row is R1 new. Okay, after doing all the operations, you will get this table. See over here, S1 is the leaving vector or the outgoing vector. S3 is the incoming vector. So instead of S1, I have S3. Okay, see, instead of S1, I have S3 here. What is the coefficient of S3? It is 0. Okay, from where did you get the coefficient of S3? Over here you have S3, the coefficient of S3 is 0. So that is why you are getting 0 here. Okay. So using the above row operations, I have the table over here. Again, I am going to check for Cj minus Zj. Here it is 0, 0. Here it is negative 1 by 4. Here it is again negative 1 by 4 and 0. So all the values are either 0 or negative numbers. So I don't have to go for further iterations. Okay, all my iterations are over. Okay, over here I have the value of z. Okay, how do you get this value of z? You are actually multiplying each column of CB with each column of x1, x2, s1, s2, s3 and xb, right? So when we multiply 0 into 4 plus 1 into 2 plus 2 into 3 by 2, I get a value 5. Okay, so this is our final simplex table. The answer that comes over here is the value of z. Okay, so z is there, z is equal to 5. Then we have x1 is equal to 3 by 2, s2 is equal to 2. Okay, hope this is clear for you. X1, how did we get? This is x1, the value corresponding to the solution column. Okay, here it is 3 by 2. Okay, this is the solution. Solution column 3 by 2. Over here I have x2. The value corresponding in the xb column it is 2. Okay, so I have x2 is equal to 2. Okay, hope it is clear. Okay, now I'll just show you one more thing. I'll just show you. See, we already told that degeneracy situation happens because we are having a constraint. The constraints are not framed properly. Okay, so this is the same problem. Okay, this is the same LPP that we solved before. Okay, in the simplex table just now. Can I show you once again? See, this is the problem. This is the problem that we just now solved. Okay, here we have 4x1 plus 3x2 less than or equal to 12. Okay, I'm just drawing the graph of this LPP. I'm drawing the graph of the LPP to show you how the constraints are coming. Okay, so this is the same LPP problem. Here I have the second constraint is 4x1 plus x2 less than or equal to 8. Over here also I have the same constraint. This is 4x1 minus x2 less than or equal to 8. Okay, here. Okay, third constraint is this one. Third constraint is the same here also. So I'll show you how the graph comes. Okay, for plotting the graph, what should you have? You should have 2 points that is corresponding to each constraint. Okay, how do you get the 2 points? We have already discussed. In the first case, put x1 as 0. Okay, in this case, when x1 is 0, this variable will become 0. Okay, so it is 3x2 equal to 12. Okay, so x2 is 12 divided by 3, which is 4. So that is how we got this value. Okay. Okay, this value we got. Again, for getting the next value, put x2 is equal to 0 in this constraint. Okay, x2 is equal to 0, you will not have this term. Okay, so x1 is equal to 12 divided by 4. So 12 divided by 4, it is 3. So x1 is 3 when s2 is 0. Okay, we have already shown you. I have already shown you how to plot the points for a graph, right? So if you don't know, please refer to the YouTube video. Okay, so this is our constraints for each of the 3 constraints I have taken the points. Okay, 2 points are necessary for drawing a line. Okay, each point will have a x coordinate and a y coordinate. Is it clear? Okay, so using this first constraint, okay, I'll show you the graph. Okay, the first constraint is this one. So I have drawn the line for the first constraint. Okay, this is the line for the first constraint. Okay, this is the line. Okay, this one is the line for the first constraint. Okay, now what have they told? The first constraint, the inequality is less than or equal to. Okay, so I'm going to shade the portion this side. Okay, I'm going to shade this portion. Okay, this portion I'm going to shade because this is the line corresponding to the first constraint. The inequality is less than or equal to, so I will shade the below portion. Okay. Okay, so I have shaded this portion. Okay, I will not shade after this because why? Because x1, x2, x3, everything is greater than 0. So all your shading things should stop in the first quadrant itself. You should not go to the other quadrants. Okay, for shading, it should all stop in the first quadrant. Okay, next one, my second constraint. This is my second constraint. I have written a second constraint. Okay, so the graph corresponding to the second constraint is this one. Okay, now I'm going to shade that below region. Over here, second constraint also has less than or equal to. So I'm going to shade the region below the graph. Okay. Okay, so I've shaded for both the constraints. Over here, you tell me what is the common region. The common region has both the lines. This is the horizontal line as well as the vertical line. Okay, so this region is going to be the common region. Okay, the quadrilateral formed by these 4 points will be the common region. Okay, I'll just shade it. So this is the common region that is formed by constraints 1 and constraint 2. Okay, this is the common region. Now we'll check for constraint 3. Okay, constraint 3 has a graph like this. The line is like this. Okay, over here again we have constraint 3 also has less than or equal to. So I have to shade this line, this portion. Okay, this is constraint 3. I have to shade this region. Okay, I have to shade this one. So I'm just shading it. Okay. Okay. Now what to understand this? Even though we have a constraint 3 coming here, we don't have any change for the common region. Okay, the common region just remains the same. Okay, the common region earlier was formed by constraint 1 and constraint 2. Okay, the graphs there, the first and the second lines that we drew. Okay, we got a common region. Okay, I've shaded it with dark line here. Okay, now third, I have drawn this constraint number 3. Okay, even though I have introduced constraint 3 here, there is no change for my common region. Okay, common region remains the same. So what do you understand? This constraint 3. Okay, it is a redundant constraint. Okay, did you understand? The constraint 3, even if I introduce constraint 3, there is no change in the common region. Okay, the feasible region remains the same. Okay, so there is nothing is contributed by constraint 3 to the feasible region. So I call that constraint 3 is a redundant constraint. Okay, is it clear? Just check the constraints over here. 4x1 plus x2 less than or equal to 8. Again, they are telling 4x1 minus x2 less than or equal to 8. Is that possible? No, it is not possible. Okay, for example, if I tell 3 minus 1 is equal to 2. Okay, can I tell 3 plus 1 is equal to 2? I cannot tell. Okay, so this one is a redundant constraint. Okay, similarly, in our case, third constraint is the redundant constraint. Okay, it is because of this situation that we have the problem of degeneracy.